Okay, so welcome everyone to today's webinar. It's my pleasure to introduce today's speaker, Rosario Paradiso. So Rosario got his PhD from Department of Mathematics and Computer Science at the University of Calabria in Italy, and then joined the Free University of Amsterdam in the Netherlands as an assistant professor. His research is on exact algorithms for combinatorial optimization problems, both on the deterministic, but also under uncertainty, and mainly focusing on applications in supply chain. So without further ado, I want to give the control of the mic and the screen to you, Rosario.
Thanks a lot. Thanks for the introduction, and also thanks for inviting here. I think it's a good and nice opportunity to present at the webinar. Okay, so the talk that I will present today is a work on which I work with Angelos Georgiou, who is here, from the University of Cyprus, but maybe you already know him. Said Dabia, a colleague at the FU, and Denise, ex-colleague at the FU, she now works at Ortec indeed. And before going into, let's say, the theory and the math of the work, I would like to introduce the problem, but a bit telling you how this collaboration started. So how we started working on this. And we started from an hospital. So when I moved to the FU, there was this NWO project in which one of the pilots that were within the project was to solve a problem at the hospital. So this is the Al Rijn Hospital in the Netherlands. It's a big hospital in the Netherlands, and they had an issue. The issue was that when they were getting medicine from a pharmacy, so when medicines were delivered to the department of the hospital from the pharmacy, some of the crates that were used to deliver the medicine, they were never brought back. So these crates were somehow lost somewhere in the hospital. And the idea was, so these crates, because they were delivering medicines, so they were containing medicines, they had to contain these transmitters that you see here in the middle. And these transmitters were there to record all sorts of information about the temperature, if the crate was open, so the light going in the crates, or if in general the status of the medicines, okay? Because there were actually requirements on how the medicine should be delivered. And these transmitters would give all the information the moment they were close to a sensor that you see here on the right. And the problem was all these crates with all these transmitter and sensor were never really, not never, but many of them were lost around the hospital. And the hospital was not a small building. So here you see a map of the hospital. There are several floors, and every floor was actually quite big. So the problem was a bit, okay, we don't know how, or we should inspect the various departments of the hospital to recollect back these crates. But then the idea was, can we somehow use the information that we have from the sensor, that the sensor take from the transmitters to locate the crates and somehow optimize this process of getting the crates back. And that was a bit what inspired our problem. And so we said, okay, we could effectively say we could place some sensors in the hospital, and this sensor will tell us where the crates are. And after we could schedule or decide or where to go to collect these crates. And after that, you will have missed some crates, but the idea was we can probably collect more crates than what is normally done, instead of walking around and visit all the departments of the hospital all the time. So this situation, let's say, inspired what was give us the inspiration to, in a way, generalize this problem and look at what we call the sensor placement orienteering problem. And this is also our main working example in our paper. So this problem combines two optimization problems in a way that you have to solve in an integrated manner. So you have the sensor placements, so how to collect information, so how where you want to place sensors, and the orienteering problem. Now, the orienteering problem is a classical, if you want, problem in the routing literature, in which you have a set of points, of nodes, locations, whatever you like. And the idea is that every node has a profit associated with it. And what you have to do, you have to design a route that visits the set of nodes in order to maximize the profits that you collect. Given that, of course, the route that you design is subject to a maximum length. Yeah? So, for instance, here to a maximum length. So, if you combine this problem with the sensor entity problem, you will have a problem in which you first have to put some sensors on the nodes. So, in this case, my black squares are the nodes where I have decided to put the sensors. The moment I put the sensor, I have observed the profit of my nodes, which in this case would be under uncertainty. And then after that, I will decide some routes, and these routes are designed in view of the fact that the profit on the nodes for which I have decided to observe is known, but the other is still under uncertainty. So this is a bit the problem that was inspired by this hospital example of this pilot. But if you think about it, this setting has many more applications. So in against the, or even if you think about wildfire detection, you could see the sensors as drones to inspect the area. The profit of a node is the urgency of the amount of how much important is to visit a location with your vehicle to fight against the fire, and the node that you have to visit can be seen how to route your vehicles there. So there are many other, in principle, every application from the orienteering problem, or many of them, can be used in a setting in which you combine this with sensor placement, okay? But if we look at this problem, so at the problem that I just explained, of course it's a problem under uncertainty. But there is, if you wish, another level of complexity is the fact that uncertainty is not exogenous to the process. So now I would just like to briefly mention what's the difference between exogenous and endogenous uncertainty, and then explore also the literature. So let's have a look at the static robust optimization problem and an adjustable robust optimization problem. And I will also use this slide to define my notation here. So from now on, Xi is always the vector of the uncertain parameters. X are typically my first stage decisions, and Y my second stage decisions. So if we look at these two problems, what you see that here, there is nothing you can do, or your behavior doesn't directly affect uncertainty. In other words, this Xi here doesn't change, or you cannot affect it with your first stage decision. So in other words, in these two problems, uncertainty is exogenous to the optimization decisions. But if you look at our problem here, this is not true, right? And we then move into the realm of endogenous uncertainty, in which indeed uncertainty depends on the optimization decisions. And actually, the seminal paper, it's quite old, but it's also interesting that at that time they were describing these entities that they are giving more information about the probability distribution as indeed as sensors. They were also calling them sensors. But anyway, if we dig a little bit into the literature, mainly in stochastic programming optimization, the papers, they have described two types of endogenous uncertainty. So the first one, in which you can affect the outcome of uncertainty, in this case can be probability distribution of uncertainty sets. And type 2, in which you basically can change or influence the time at which uncertainty is observed. And this is our case in this work, because when you place a sensor, somehow you are moving when you will observe the information. You're changing that. And typically this, or in more recent papers, this has been name in the robust optimization literature. Type 2 as named as decision-dependent information discovery. And this is where we are in terms of problem setting. If we look, so what's the meaning of this? So let's put everything on a timeline. I just want to get rid of my Zoom. Yeah, here. And let's see what's the sequence of the actions here and the role of uncertainty. So I have in this case, in these problems, you normally have, or you could have, two types of first stage decisions. The first type, the X can be like a standard type of first stage decision, for example, open your facilities. But then additionally, if you have decision-dependent information discovery, you have also another vector of decisions, which is this W, which is by binary. This has to be binary. And here, as a first, and this describes which, or it says which components of the uncertain vectors you want to observe. After deciding that, what you are going to observe, you will observe only indeed the component of the uncertain vector for which you have switched this component W to 1. Then you will take your second stage decisions. And finally, you will observe and pay the price for what you have decided to not observe. Okay? So for this problem, Vellanos et al., they proposed a dynamic formulation which works as follows. So essentially they say, okay, as first stage decision as described here, but then after you have this maximization problem with this additional uncertain vector xi bar, which you observe in full anyhow. So you are going to observe this xi bar. You are going to take your second stage decisions. And at the end now, the xi has to belong to this new uncertainty set here, which depends on W and xi bar. And this new uncertainty set says the xi has to be in the original uncertainty set, but the component for which we have switched W equal to 1 has to be compatible with the xi bar. So essentially, if you have a Wi equal to 1, you are enforcing that xi bar I should be equal to xi I, and therefore it means that you have observed xi I already here. Okay, so that's how they formulate this decision-dependent information discovery problem. And after that, actually, other papers appear. So, in terms of methodology, they use the k-adaptability approximation. Then Omer et al., they define some nice exact compact formulations that are, some compact formulations that are exact under some assumptions. And also, there is a solver for multi-stage robust problem that can be applied to the DDA case under discrete uncertainty. If we look at if you look also at the literature about stochastic programming, we also see that there are several applications for this type of problems. For example, for the Dutch friends of people living in the Netherlands here, I don't know if you know the stemvisor. So essentially, what you do here, this platform or software, whatever it is the idea is that it says what you should vote, which political party you should vote. And you get some questions. You have to say if you agree or disagree or skip it. And after that, of this set of questions, they will tell you, okay, you should vote for this party. And you could look at this problem. So our W variables in this context can be seen which question you should ask in order to later on give the party that better matches the preference of the idea of the person. Another example, when you think about wind resource assessment. So essentially here, the information about the wind in a certain area doesn't come for free. If you don't go there and pay and conduct a study, to see how the wind behave in a certain area, you don't get this information. And so this is an example in which in order to get the information, you have to pay, okay? And there are many other examples. For example, many other applications, if you look into workforce planning, humanitarian relief distribution, and so on. There are actually many cases in which if you don't pay, you don't get this information. Okay, so when we started working on this project, what we saw that many of the work, or most of them, they focused on conservative approximations without performance guarantee. And what we thought is that, first of all, we could design some exact algorithms to assess the accuracy of these schemes. But also, we also saw that the problems, even approximate schemes, were actually difficult to solve. So we also say we could try even to improve this approximate formulation to approach larger problems. So what we did, we designed an exact algorithm for this class of problem. We tried to improve the k-datability. And when I speak about improving, I don't mean that the quality of approximation is improved, but that we make it easier to solve, so more efficient to solve it. And by combining the exact algorithm, by using the exact algorithm and the k-datability, we also studied what's the relationship between adaptability and information. We also studied some extensions, but I won't talk about that in this talk. Okay, so I would like to then proceed with the exact algorithm. So the idea of the exact algorithm is using the compositions. In principle, what we do here, we combine logic benders and column and constraint generation in a nested way. And we looked at the problem in this way. And from now on, I will assume my first stage decisions are only discovery decisions. But later on, I will also briefly discuss how we could extend this to the case in which we have other type of decisions. And also, our applications or our working examples assume that Y is binary, so it's a combinatorial set, but in principle, we don't have to. It's not really required. So the idea is to look at the problem if you want decomposed, and then another level here that decides on the W. And then in order to optimally decide on the W, you need to solve this problem to get the value of the function for the given W. Yeah? So I will first discuss this part, how we deal with this outer problem, which I will name master problem, and then I will discuss how we actually evaluate this phi of W in order to formulate this problem here. So the idea of the master problem is to use, the general idea is to use what they call logic bender cuts. So essentially what we want to, these cuts are made in such a way that they are tight at every binary points, and they are an underestimation at other points. So in principle, what you see here is that this cut here is defined in such a way that if I would evaluate my cuts, so first of all, they are written in principle for every W in the feasible set of my discoveries, and they are made in such a way if I would evaluate my cut for W prime here, I would exactly obtain the correct value function. But if I would evaluate this cut at another W, I would get an underestimation on the real cost of this other value. So this is the general idea. And in order to achieve this, you need this lambda W prime W. In short, essentially what we do here, we say, okay, we make sure that we have a convex envelope that is tight at all the integer points of the feasible space. And this makes sure that you will have to add these cuts in a dynamic way because they are exponentially many. But typically, But what we do here, we embed this in a branch and cut. So essentially, we have our branch and bound algorithm, and every time we encounter an integer solution, we check if we have to add the cut by actually calculating this value, this phi of w prime. So this indeed requires that at every iteration, if you want, you need to go and solve a problem to get this value of phi w prime. And this is what we essentially do into the slave problem. So now imagine that in our outer algorithm, we have encountered an integer solution, and we have to check if the current cost that our model about the cost of our current solution in our model is correct. So the way we have to do, we have to go back here and actually calculate this phi of w, which we need for our cuts. And now if you look at this problem, you could see that this is essentially a two-stage robust problem in which the role of uncertainty and the decision maker is switched. And so you see here that we have uncertainty is deciding on xc bar, then we decide on y, and then uncertainty will decide on xc in this different uncertainty set. So that means that we could reformulate this problem. We can say, okay, let's start from a subset of the second stage decisions. And you can reformulate this problem in this way. The way we solve this, we dynamically enrich this set until we have converged, like in a classical column and constraint generation algorithm. And the moment we have converged, we can claim, okay, now we have the value of this phi w. And then we can go back in our master, define our cuts, and continue. So the good news about this problem, it's true that we have to solve a second two-stage robust problem for every cut that we generate. But at the same time, this problem, when xc is continuous, is a large LP. So it's not a MILP. Okay, so here the combinatorial this problem is not a MILP, but it's just an LP. Okay. Okay, so what's the problem with all this approach is that the logic bender cuts that I have presented in the master, they are typically very weak in the sense that you may need a lot of them to converge because essentially they are tied at the integer point, but the linear relaxation is typically very weak, so you need many of them. So in order to improve over this, because otherwise we would just almost enumerate all the W's, we propose a stronger family of cuts to use instead of the logic bender cuts, and an alternative master problem, which we name hybrid decomposition. So I will start first from the information inequalities. And so the information inequalities, they somehow they are valid. They are not always valid, first of all. They are valid only in problems for which give me two W's. If W1 has more information than W2, so has a superset of components equal to 1, then what has to happen is that our function phi in W1 is less or equal than W2. So in other words, this means if you have more information, you cannot have a worse objective function. Okay. So under this assumption, what we can do, we can redefine our cuts. We can get rid of this first part here and redefine these cuts, our cuts in this way. So essentially now we redefine this row of W prime W, in which we only account for the component of the vector W prime that are equal to 0. So in the paper, we show that these cuts are not cannot be dominated by the original one. In practice, on a little numerical example here, so on the left, you have the envelope built by that you obtain using the logic bender cuts, and here you have the envelope using the information cuts. And you can clearly see that, first of all, the cuts, they reach achieve the same value of the integer points, which is what we expect. But also that here, the logic bender cuts here, you see that this area is completely flat. And so here you see that the linear relaxation, all these points of the linear relaxation, they achieve a way lower value than here, where you see that the cuts are somehow tighter and closer to the real objective value. So essentially, the idea here is that these cuts bring an additional inject additional information in the model by saying if you have a solution with more information has to go a solution with less information, sorry, has to cost at least has a solution with more information. So how someone else would essentially say that information is power. So if you have more information, you cannot do worse. And these cuts, they use this property, let's say, which is in most of the time true. It's a mild assumption. The second enhancement is this hybrid decomposition. And as I said, the idea is let's try to use an alternative master problem, okay? And how could we do that? So the idea is let's try to enumerate. Imagine that I could enumerate all my scenarios xi bar. So I do that. And of course, now I will have decisions y of xi bar and xi of xi bar, because those decisions are taken after observing xi bar. And if I now dualize the max, the final max, I obtain something like, I exactly obtain actually this problem, in which what I have here, for each block of scenario xi bar, I have some dual variables that I came from the dualization, and I also have some second stage decisions. So essentially, this master problem has way more information than the first master that I presented. But of course, the problem here is that every time you add a xi bar, you are gonna enlarge this problem with the new second stage decisions. This is the classical problem of the issue of the column constraint generation. But it has so what we do here, so although you could use this as another exact, right? So you could basically solve this problem and then get your W and go to the slave problem to look for the next xi bar, and this will grow every time you have the xi bar. But what we do, we combine this with our original master problem, and we collect some scenarios at the beginning, xi bar. We plug them to, let's say, in a way to warm start the model, and then essentially we stop. So we don't add new scenarios anymore, but we only add cuts. So the idea is that during the first iteration, somehow you already give good direction to the W to look for good solutions. Good solution. And the fact that we don't add scenarios on the fly anymore, it allow us to just use a branch and cut. So we just add cuts without adding new variables all the time. Okay. Okay, now I would like to switch to what we did for the k-adaptability approximation. So I will quickly go through k-adaptability in the decision-dependent information discovery settings. So what's the idea now? The idea now is that here and now we decide on our W and on our K policies. After that, we observe xi bar. Then we select one of the K policies, and finally the real vector xi will reveal and this vector will be compatible with xi bar and our W. Okay, so it's the same reasoning I explained for the exact approach. And for this problem, of course, the k-adaptability already existed, but Vallanos et al. They extended it for the decision-dependent information discovery setting. And let's say that the cool thing about cadatability is that you can reformulate the problem as a compact formulation. Okay, so you don't need all these decomposition schemes, but this is the problem. And when this y is binary, you can linearize it and give it to the solver. And then in principle, you are done. However, when you are in the DDID settings, there are additional bilinearities that in red you see here. And this problem gets also more difficult to solve. So of course, cadatability, it's even in the classical setting is difficult because you have decay policies and you have symmetries, but you also have to deal with more bilinearities here. So what we did for this problem was to, first of all, work on the symmetries. And as you will see, we focus on this variable alpha to work on the symmetries. Then we worked on the linearization of bilinear terms, so try to have a better linearization of the bilinear terms, which with the stronger linear relaxation. This will involve the gamma here and the alpha both, but I will only discuss the alpha here. And then we also defined some valid inequalities, which we named optimistic inequalities, and also how to use relaxation linearization technique to, again, improve the linear relaxation of the problem. But in this talk, I will just focus on the first two points. So for the gamma, what we did, we actually defined tighter big M to linearize this gamma. And while for the alpha, the idea is to order our policies based on the value of alpha. So first of all, if we look at the problem for given W, so this is the problem for given, actually, not only given W, but given W and Y, so given first stage decisions. This is the problem that then you will dualize to obtain the cadatability. And here, what you see that the alpha, essentially this alpha is associated to the cost, is the dual associated with the epigraphic constraint. So in a way, it's associated with the cost of your policy K. So the idea is, since you can show that without loss of optimality, you can enforce an order on this alpha. So you can order your policies based on the value of alpha. So essentially, you can add this constraint on the cadatability to improve the linear relaxation and in principle to also avoid symmetric solutions. So now solutions which have the same y would have different cost if they would not be ordered correctly. So this reduce, so you essentially order your policies. And this will show that this is valid in the sense you can do this without losing optimality. The second, when we go to bilinear terms, so here I'm focusing on the product between alpha and y, but you could also extend it the same to the alpha and w. The idea here is when you linearize bilinear terms, you can always use the McCormick inequalities. And assuming that the y are binaries, this is what you would get. So those are the four McCormick inequalities that you need to linearize the product, where L of alpha k is a lower bound on alpha, and U on alpha k is an upper bound on alpha. So in the classical cadatability problem, you could fix this L and U to 0 and 1. Why? Because if I go just 2 slides back, the 1 comes from here, and the 0 comes from here. Right? So those are valid upper and lower bound on the alpha. However, in general, the idea behind the McCormick is that if you could tighten those bounds, so the smaller these bounds, the better is the approximation, the better those inequality approximate the products between the two variables. So in a figure here, if we look at this blue plot, this is the value of the real product, between the alpha and the y. And this green plane here is the plane described by the McCormick inequalities if you set this to 0 and 1, the L to 0 and the U to 1. What we show essentially is that without loss of optimality, you could set this L to 1 over K, a capital K, if K equal to 1, and U equal to 1 over K without loss of optimality. And what you would observe, this is a graphical representation, but if you go in the paper, there is a numerical example on this, that you will observe something like this, so that instead of having this green plane now, you will have this orange one, which would get closer to the real product between the two variables. Okay, so the idea is that now I would like to switch to some computational experiments to show what's the benefit of using our exact approaches and comparing the exact approaches with the k-adaptability problem. So the first set of experiment is for the sensor placement orienteering problem, in which the networks are from the literature up to 30, around 30 nodes. And what we do, our uncertainty set assumes that every node has a profit between 0 and U, but the sum of all the profits over the sum of the total profits over the network is equal to 1. And clearly U is a number which is less than 1. And the feasible set of the discovery information is, so we have you can observe up to a fraction of the number of nodes. So in this case, we have different experiments. So we assume that you could, in some experiments, you can observe up to 25% of the nodes, 50% and 75%. And so what you see here in this first plot is the performance of the k-adaptability and the exact. So what we did here, we gave 2 hours time limit to all the approaches, and we then compare the best solution obtained within 2 hours with the best global lower bound on the problem, which was provided by the exact. And what you observe here, that of course the gap of k-adaptability decreases when you have more adaptability, and that the exact, actually that the optimality gap of the exact is quite small. So within the same time frame, the exact was actually able to give better solutions. But what we wanted to inspect also was, okay, why do we get this suboptimality gap of k-adaptability? So from where does it come? Okay, so in this slide you see 3 solutions of the orienteering problem: 3 adaptability, 4 adaptability, and the exact. Of course, for 3 adaptability and 4 adaptability, I also have the 3 and 4 policies. While here, of course, you have many routes, so I'm not plotting them. And what we observe here, that here we have 3% for 3 adaptability, 5% for 4 adaptability, and 7.7 for the exact. But what we also did, we asked ourselves, okay, why do we have this optimality gap? Because if you observe the way sensors are placed is also different. So we said, okay, maybe if I take the sensor placement of 2 adaptability and I evaluate this sensor placement exactly, maybe I would get this same optimal solution. And that's what we tried. And what we observe is that of course, the objective function improves. So in this case, we collect more profit, but we still don't reach the same performance of the exact. So essentially here, the message was, when you approximate your second stage decisions, what's going to happen is that you are going to also take suboptimal first stage decision. In this case, suboptimal first stage discoveries. This is something that we also observe maybe from another angle, is that this relationship between information and performance. So this is an example based on is an instance inspired by the hospital example. And what we did here, we said, okay, let's try to solve this instance with all our approaches and we give zero information, so zero sensor here, up to full information. So you place sensors everywhere, okay? And what you see is that, of course, when you give zero information, all the approaches, they perform the same. So why? Because effectively here you are in the robust optimization case, single stage. But then what is interesting is that if I give more information, two adaptability doesn't improve. So if I now allow to observe 25% of my nodes, two adaptability stays the same. Even if I go to 50%, even if I go to 75%, even if I give all the information. For tree adaptability, when I give 25%, it improves. So you see it goes here. But then if I keep giving more information, it stays the same. And nothing really changes. Similar in for adaptability, but it improves up to 0.05, while you see that the exact improves every time. So essentially, what we observe here is that if you don't have enough adaptability, even if you have more budget for information, this won't help you. So essentially, you cannot compensate lack of adaptability with more information. And in this, additionally, what I wanted to now, so this was comparison exact and adaptability, but now I also wanted to quickly give an overview on what's the difference between this strong adaptability, strengthened adaptability, which is the adaptability formulation with all our improvements against the traditional one. And what you see is that, so on the left, you see that the average optimality gap of the strength and adaptability is way lower. This is over all the whole data set, but also that we solve way more problems compared to the classical adaptability. And this type of experiments, I also want to show this type of results for the robust shortest path problem, which is a classical problem used in the robust literature to benchmark approaches. And in this robust shortest path problem, of course, we have also discovery decision. So the idea is that now you have uncertainty on the arcs. And the idea is that as a first stage, now you observe the cost of some arcs, then you will make your route, and then you will pay the price. Of course, for this now today, I'm only show results for adaptability because the results of the exact are pretty similar. All the takeaways are pretty similar to the orienteering problem. The instances here are the instances from the literature, so generated as in Anna Susanto et al. And Subramanian et al. And here we consider instances from 30 nodes to 50 nodes, and then we so like they do, but we don't start from 20 nodes because that they were actually easy in for our approaches. And the type of discovery, the set of the discovery decisions is actually similar to the orienteering. So you say you can observe up to a fractions of the number of arcs. And again, this was 0.25, 0.50, and 0.75. Okay, and what we can show here is that, interestingly, in this case, the gap, let's say, between this strengthened adaptability and the standard adaptability is even bigger. So, and I believe that here the complexity is less on the nominal problem, but on the adaptability problem on its own, and that's why you see this bigger difference here. So we always solve. So the optimality gap for us are always under 5%, and we basically solve almost all the instances. With for adaptability, we are around 70, but almost all the instances, while for the standard adaptability on this shortest path problem, you have at least more than 60% optimality gap and no instances solved to optimality. Still this in 2 hours, time limit and single core. Okay, so I think I'm on time, yes. So to conclude the talk, so what did we see today? So when it comes to the interplay between information and adaptability, what we can conclude is that more information doesn't always lead to better decisions if you cannot adapt. So if you would have to pay for this extra information, maybe it's not worth it. What about the suboptimality in adaptability? We saw that it arises from both lack of adaptability but also suboptimal discovery decisions. So in a way, this is telling you, okay, if you would use adaptability to try to take exact discovery decisions, you may lose something there. And when it comes to scalability, adaptability, it's difficult to solve, not always more efficient, although we all know that adaptability is an interesting problem on its own, right? So sometimes you really just want to solve the adaptability problem. And I still think that, however, exact algorithms are pretty useful when you want to study the behavior of approximate algorithm, but also the structure of the problem. Probably soon you can also read the final version of the paper because it has been recently accepted on Informed Journal Computing, and the code is actually already available in one of the repository of the journal. So thanks a lot for the attention, and if you have any question, I'd be more than happy to try to answer.